Okay, for a general process on the LHC, we have proton-proton collide with each other, and then with high energy hard scattering. With high energy scattering, and then the final soft particles will emit collinear particles and the soft particles, and so this is the general procedure at the LHC. So in order to increase the theoretical prediction, we can first resign of the soft and collinear emissions, and on the other hand, we can also increase the to compute the higher order correction of the hard scattering. And so far, we managed to compute the, for example, for two-loop 5-point integrals, and also three-loop 4-point functions, and also two-loop 6-point integrals. They are all quite complicated with the multiple scales. And in order to compute this kind of integrals, one of the powerful methods is use differential equations method. We begin with a set of differential equations and then choose an appropriate basis or canonical basis such that we can get epsilon factorized differential equations. And with these differential equations, we can further simplify, rewrite it as a D-log form, and this capital AK is just a constant metric. With these differential equations, all the solutions can be expressed as iterated integrals, and such that we can see this kernel of log or a letter, it totally determines the function space of the Feynman integrals. So it is very important to determine the letters. But with this method, we face, I think, two challenges. First is for multiple scale integrals, it is hard to do the symbolic IBP reductions. And on the other hand, even if we have the epsilon factorized differential equations, it is not easy to combine it to a total derivative to get the letters, because we have, for multiple scales, we have a partial derivative. So this is two main challenges. But on the other hand, once we have the letters, we can gain some benefit. First of all, we can use it as an input to find the canonical basis. Also, we can just bootstrap the coefficient, the coefficient of the letters, such that we can get the canonical differential equations. And furthermore, we can just use these letters as an input to directly bootstrap the Feynman integrals. So this is the benefit. And due to the importance of the letters, much effort was to investigate the letters. For the one-loop integrals, it is fully understood from different perspectives. And for the two loops, attempts are made from different perspectives. First off is Landau singularities, and I think use the modern mathematical tools, we can just investigate the pinch pole and get the singularities of Feynman integrals. And I think today there are two new nice papers about these Landau singularities. And sorry, I didn't add a reference because I sent the slides yesterday and I can't have chance to add it. And Schubert problem is another promising method. It is trying to solve the Schubert problems, and the letters can be rewritten as a cross-section of these solutions. And it can, with this method, we can bootstrap the irrational letters and the rational letters. And some other attempt to understand the letters, it is use the intersection theory. to study the D-log or D-log form of the integrand and get the letters. Okay. Then since my talk is about get the letters directly from the grand determinant, I should first explain the Baikov representation. Actually, it is just a change of variables from the component of loop momentums to the scalar product of the loop momentums. So for each propagators and irreducible scalar product, we'll introduce variables, and this grand determinant is just from the Jacobian, and it is just a determinant of the scalar product of the external momentums and the loop momentums of momentums. Okay. But with this representation, for example, for the subsector integrals, usually we need to introduce much more unnecessary variables. So it is not a convenient representation. Usually we use the loop by loop. We start from one of the loop momentum and view all the other loop momentum as external momentum. And then we apply the standard Baikov representation. We can get the representation for this loop. And we continue to the other loop momentum and we'll get the representation. And it can write as a general hypergeometry function. And this is the twist, and it is just a product of some grand determinant. This P is some arise from some grand determinant. And because we have two different representations, so there should be some relations. Actually, it is we can start from standard Baikov representation and integrate out some of the variables and get some other representations, loop by loop representations, such that we can get a relation graph of the Baikov representation. This graph is just an example from two loop integrals. Okay, with this Baikov representation, one of the good things is we can see all of the whole of the propagators, it is manifest. And usually we will study some maximal cut integrals or something like that with this representation. It is very convenient. Okay, then let's see an example. This is two loop sunrise integrals with this x1 and x3, it is the propagators. And in order to define the integral family, we need to introduce two additional scalar product or ISPs. This is 2. And here is the relation graph of Baikov representation. And now here for this yellow part, here is the Baikov representation. Let's first look at the standard representation. It is just a grand determinant of all of the momentums, including the loop momentum and the external momentum. And for this U1, it is the top sector. And it just have the propagator of 1, 2, 3. And with this, okay, let's see. We can first view L1 as external momentum. So we'll get for the loop momentum of L2, we can get the Baikov representation of L2. And then we continue and we'll get L2 and view L2 as loop momentum and get the Baikov representation. And with this, we'll introduce here it just means we integrate out x5. And here is the loop moment representation for the top sector. We can also integrate out x4 and get the other representation. And we can continue these steps and we'll get all of the Baikov representation along this path. Okay. Now let's turn to the letters. Let's first look at the rational letters. Before looking at the general structure of the rational letters, let's first look at the one loop integrals. Because usually the letters is related to leading singularity. Okay, now for for the integral with even a number of external momentums, the canonical basis or de-log form integrands can be rewritten as this way. This square root is just to compensate to make it a de-log. And because the grand determinant is a polynomial, quadratic polynomial in all of the variables, you can check this integrand is really a de-log form. And now the thing is, this leading singularity will get a pinched pole at all the, if the grand determinant is 0, the pole from grand determinant will pinch with the propagators. So it is very similar to the Landau singularities. So, and if you look at the letters of one loop, you can see the rational letters, it is just some grand determinant localized on some or maximal cut of the grand determinant or localized as some poles. We'll find the very similar structures in higher loops in integrals. So the idea is just to analyze the pinched singularity of the maximal cut integrals. Here is just one folder integrals, an example. These three polynomials are all from grand determinant. And we can see this z-1 and z-b, it is just a simple pose. In our analysis, we just analyze the simple pose. And let's consider this simple pose that equals a, and we'll get, if we localize the other grand determinant on this singularity, we'll get two polynomial. One is a minus 1, and the other one is this quadratic polynomial. But the thing is, they all can be rewritten as some grand determinant localized on some poles. And with this, we can see we'll get some pinched poles. So it is really, really related to the Landau analysis. Okay, with this relation, we can get all of the rational letters or candidate of rational letters. Okay, now we still take the sunrise integral as an example. At the top topology, we have U1, the back-of representation of U1 and U2. Now for the U1, after the maximal cut, we have four grand determinant. And if you look at now the thing is, these two, the power of these two is half integer. We just set epsilon to 0. And the special thing is for this L1 and 2, grand determinant of L1 and L2 at maximal cut, it is a perfect square. So we'll get a simple pole at x4 equals m1 square, and also a simple pole at x4 equals 0. Now the thing is, okay, for this pole, we can localize this grand determinant at, okay, sorry, it should be m1 square, sorry. And we'll get some Kähler function. This is just the Kähler function. And we can also localize grand determinant of L1 and L2 at 0. We'll get another pose. And we can check these two. It's really the rational letters in the differential equations. But the third one, it is a little special because we can localize grand determinant of L2 and P on this singularity. We'll get S minus M2 square. The things it is not it is a superior pole because the thing is, if we set Landau singularity Landau discriminant to 0, then the Euler characters or number of master integrals should decrease. But we can see this indeed decrease the master integrals in the representation of U1. But if we look at U2, it is not. So the third pole, it is not it is a fake pole or spurious pole. So it is not a rational letters. Okay. So we can see it is the general structure of rational letters. Now let's turn to the irrational. The thing is, I think the way to construct the irrational letters, it is the key point to construct the irrational letters is list identities. Okay, thank you. List relation Sylvester identities is related different grand determinant. Okay, then the thing is once we locate this relation to some singularities, we can get the different relations from different rational letters. And because it is this identity is a quadratic polynomial in by a grand determinant, so we can, similar to the construction of the log form, we can construct these two kind of the log form. We can, okay, here we assume all of these DE and all of the grand determinant as independent variables, such that we can construct these two kind of things. And finally, once we construct the log form, we can just localize this log form to some single some point or maximal cut. Then the kernel of this log will be just the irrational letters. Okay, but this is the general construction. But we will construct a lot of letters. We need to impose some selection rules to select the symbols. It really appear in the canonical differential equations. First of all, it is because this square root. First of all, the thing is the power of grand determinant in the back of representation should be 1/2 if it is appear in the square root. This is very obvious because we know the leading singularity. Because when we construct the log form, we localize to some singularity, then we'll get some the power of the grand determinant should be compatible with the back of representation. Sorry. The other thing is all of the grand determinant appearing in the square root should be linked by the row of the row in the graph of the relation of the recursive in the graph of the relation of back of representation. And finally, we should impose that it is not a perfect square. Of course, it is. Otherwise, it will be rational. Okay, with these three criteria, and we can construct all of the irrational letters, and we write a mathematical code, and you can find it on GitHub. Okay, now still with the sunrise. Okay, now the thing is, the power of the grand determinant is half integer. We have this grand determinant, and then we can construct some of the, for example, we can construct these two, and it really gets the irrational letters appearing in the differential equations. Okay, this is the example for sunrise, and because for sunrise it is really easy and it is not convincing, so we apply our code to some multiple scale integrals, and list 3 is just the 5 point with one massive external momentum, and we have checked all the letters appearing in the canonical differential equations, and also with my package, and this is the 5 point, but with two massive external and one massive propagators, internal massive propagators, and we also check this two different 5 point with two different masses, and it has 127 master integrals, and we construct the canonical basis and then use the numerical way to bootstrap the canonical differential equations, and we really find a perfect agreement. And here is all the 43 rational letters. And you can find, okay, let's look at the last one rational letters. It has 4 lines. You can see it's really complicated. So it is not easy to construct the letters directly from the canonical from the partial derivative. Okay, then the thing is we also for this integral we also get 62 irrational letters. This is one of the example. It is constructed from these D-log forms and imposing the singularities like that. And this is for two loop 5 point. We also look at 3 loop 4 point integrals. And with these integrals, we have checked with the canonical differential equations. And and in this case, it is much simpler. We just have 2 irrational letters. And for the other 3, we bootstrap all the letters, but we leave the check with in the future, I think. Okay. Okay, this is the okay, in this talk I introduce the recursive structure of the backward representation and present the algorithm to extract the symbols, and also check with the bootstrap the 2 loop 5 point and 3 loop 4 point integrals. And so I think it is for the outlook. I think it will be very interesting to explore the relations for different method, I think, especially with the solved problems. Also, because when we extract the rational letters, we investigate the pinch pole of the backward representation. So it is very interesting to investigate the Landau singularities. But I think people will talk about this maybe in the afternoon, or in the later talk, I think. And finally, we would like, once we have the letters, I would like to see whether we can just directly bootstrap the analytic expressions from the letters. Okay, this is my talk. Thank you.
Thank you for the very interesting talk. Questions? Over here.
So it's known that for sunrise integrals, the Landau singularities are hyperplanes in the space of p squared and masses. How would you interpret geometrically those square roots that you have in your symbols?
Sorry, can you?
How there are the square roots that you see in your symbols in the forms? Is there? Yeah, like this square roots over there.
Yes.
How would you interpret geometrically what's happening on your parameter space?
Sorry, I didn't get your point.
Well, the point is that this looks like a double cover. It's like a branched cover over some locus.
Yes.
So, and I was wondering if there are some more like
yes, because for the irrational letters, it is always some square root, and it is compatible with the rational letters or Landau singularities. But then things, just like you said, is a branch cut of or double cover of this. But then the thing is, it is if we just look at rational, the thing is how can we get this okay, sorry. How can we get the irrational of this from the things?
Yeah.
Yeah.
Thank you.
More questions? Lorenzo?
Can you make a statement about when you're able to find all the letters? I mean, does it always give you all of them, or in which cases it doesn't? Do you always have to check, say, with differential equations and so on?
Okay, another thing is because so far we just make some answers like that, and of course just okay, in most of the cases, at least in the slides I present, all the cases I find all the letters, but in some cases like I think 5-point integrals will get some nested square root or something like that. So it is beyond the answers of our of our answers. So it is in need to further investigate how to get this kind of letters.
Okay, more questions? One here.
I just remember that from two, you may get a single letter starting the cubic term, the cubic root. So can you come the cubic root with your methods here?
What do you mean cubic root? It is in the does it involve the elliptic integrals?
No, I mean that in the two case, there may be a single term which is multiple law, but there is a cubic root in the single letters.
Okay, the thing is, because for this grand determinant, in multiple case, it can be a higher or triple polynomial or quadratic polynomial or fourth order polynomial in Mandelson variables. But no, but the thing is, I think the most important thing is this: if we build grand determinant as independent variables, it is always a quadratic polynomial, such that we can construct it. And for the case with higher order polynomial, it is okay. Maybe we can just look at this example. Okay, I think there should be something. Sorry, I can't find it, but in some cases, there should be some medicines to the fourth power or something like that. So it is still possible to construct this kind of letters.
Okay. I see a mass to the fourth on the corner over there. But
Okay.
More questions? If not, let's thank Xiaofeng again.